Oh, welcome to chapter 2. We're going to talk about atoms and elements for this chapter. Go over a bit of history. So, maybe you've heard the whole thing where if you take something, you break it in half, you break that in half and half, and keep on going, you can go forever. Well, that's not entirely true. For something like a piece of carbon, break it in half, eventually get to a point, if you break it in half, it no longer becomes carbon. We call that point an atom. So, the atom is the ultimate particle of an element, and it originally came from the Greeks. So they haven't come up with the ideas of atoms, but they thought of earth, wind, fire, water instead of the 118 elements that we know of today. And pretty much anything that's here on Earth that is of any importance is made of matter. At least the stuff, or I'm sorry, made of elements or atoms. Matter is made of atoms. There's other forms of matter. That's kind of above and beyond this class. But atomic matter is what concerns us the most. It's what matters the most. It concerns us the most, I should say. So let's talk about the proof of atoms. And for us, we more or less we I occasionally get students that never heard of atoms before, but most everyone is very well versed with atomic theory. Some of the theories, like germ theory, to describe illnesses in atomic theory, these are all very mainstream. So, not too many people believe that evil spirits cause disease anymore. But for atoms, and it was a big deal that if atoms exist or not, because I mean it is kind of a hard sell, right? There's these really tiny particles, and they make up everything, but you can't see them. So people really had to talk about the proof. We can see them now, we can image them, but it was a very hard sell. And part of this started off with Brownian motion. So uh, Robert Brown noticed that there was some motion that came in from just looking at suspended grains. And where was this from? And it turns out it actually is from atoms. But we're not going to go too far into this, but it explained Brownian motion with that and included atoms. And looking at atoms here, you can see this is an image. This looks like a scanning tunneling microscope (STM) image, and I say that because they look kind of like pimples, and atoms are actually more spherical, but the imagers, the STM scanning tunneling microscopes, they kind of make the atoms look kind of like pimples. There's also atomic force microscopes, AFMs. They tend to make the atoms look more like the candy corn kind of thing. They're very spiky, but we image them. So this is not we're not actually seeing them. We're imaging them, and they're much smaller. Atoms are smaller than visible light, so we cannot use visible light to observe individual atoms. And I mentioned in the previous video that there were 92, 93 elements. It really depends on your opinion, and the number honestly doesn't matter that much. So 91 here. They're probably not counting technetium, or maybe not promethium. But like for instance, there's a scientist named Darlene Hoffman. She found natural plutonium in a sample, and it was estimated that there's about 20 grams of natural occurring plutonium on Earth. Plutonium is element number 94. And if there's plutonium, that means there's going to be neptunium as well. So that's element number 93. So it's kind of like, it depends on what you want to argue. I mean, it doesn't really matter all that much. But we've made many of them, and the as you get heavier and the super heavy elements, we don't really use them for anything. The actinides, that's the uranium, thorium, and the bottom of the periodic table. We use a lot of those for either nuclear reactions or nuclear weapons. So, but many of them we don't really use for anything. Maybe we used to use thorium because it's a very high melting point, but we don't typically use thorium anymore because of the radioactivity. But that's where we get we have 118 elements and 90-ish naturally, depending on your definition of natural, I suppose. So, and I mentioned before, the Greeks came up with the idea of atoms, and They were kind of, I mean, it's good guess. I mean, they were spot on. They were wrong about the number of atoms. We have 118 elements. There's more than just four: fire, air, earth, and water. Those four elements. There's more, much more than that. And those, of course, are not elements either. Like at least for what we consider elements. And but that's a good theory. The four elements of matter. That's a very good theory. It's of course it's dead wrong, but I mean it explained quite a bit of phenomena. And then further on, Dalton had the very strong atomic theory, and that's mostly what we have atomic theory based off of now. Although I mean Dalton was wrong as well, but we'll get into that later. So well, where did the atomic theory come from? Came from these rules: law of conservation of mass, that is, matter is neither created nor destroyed in a physical or chemical process. Law of definite proportions and law of multiple proportions. So the law of definite proportions says for a specific compound, the ratio of the elements do not change. And then multiple proportions are for two or more elements, you can have various compounds but they have different proportions. So that's the law of multiple proportions. So Dalton took all of this and said, hey, you know what? Let's take it one step further. There's atoms, they're ultimate particle of an element, and then here are some properties of the atom. So we'll get into that. And mentioned last lecture, Lavoisier and wife. Lavoisier, the Lavoisiers did the law of conservation of mass. I like that story. It's a love story that they extended to the laboratory. So interesting French nobility. And it means matter is neither created nor destroyed, just in a physical process or chemical process. So, for instance, here we have sodium reacting with chlorine to make sodium chloride. And the idea is the number of atoms are conserved, they just were exchanged. So, since each atom weighs, well, to Dalton, they weigh the same. They're about the same. We'll talk about isotopes later, but the number of atoms in each type does not change, therefore, the mass is conserved. And then Prost came up with the idea of law of definite proportions, that for a specific compound, the ratio of the elements are the same. And for instance, water is 8-1 for oxygen to hydrogen. So for that. And okay, so let's look at it. We saw that mass ratio of nitrogen to hydrogen and ammonia is 4.7-1. If a sample contains 10 grams of hydrogen, how much nitrogen it has? So if it's 4.7-1 nitrogen to hydrogen, that means that, and it's just ratios. So it's 10 times the hydrogen there, so it's going to be 4.7 times 10, or 47. So then the law of multiple proportion, and when you have two different elements, you can have different compounds with different ratios. So to tell you a really terrible joke, really chemistry jokes, they're always tough to listen to. So two chemists go to a restaurant and one says, you know what, I'm just going to have an H2O. The other chemist goes, I'll have H2O too. And the other chemist dies. And the joke is, of course, because H2O is water, but H2O2, that's hydrogen peroxide, so hydrogen peroxide is toxic, so therefore he dies. You can laugh yourself silly at home now, students. You're allowed to do that, of course. But that's the idea of multiple proportions. So you have hydrogen, oxygen, and when the ratio of one atom oxygen to two atoms hydrogen, you will get water, and then two atoms oxygen to two atoms hydrogen, you get peroxide. So, and notice I'm not saying 1-1 for peroxide. Oh, that would be proper, but if you look at carbon, for instance, you can have for acetylene is 2 carbons, 2 hydrogens, and benzene is 6 carbons, 6 hydrogens, and so they're both carbon hydrogen. So you can get various molecules off the same ratio. So that's one of the reasons why I'm being very exact with that. But that comes future. So another example: carbon monoxide and carbon dioxide. So these are two elements with different ratios. That's the raw definite proportions, and each of these ratios are specific, and therefore that's includes the law of definite proportions. So, and this is further explaining that right there, definite proportions. So Dalton atomic theory. So Dalton said each element is composed of tiny indestructible particles called atoms. This is mostly right; they're not indestructible. And all atoms of the same element, of the given element, have the same mass, and the properties distinguished from the other elements. That's mostly true. We'll talk about isotopes later. Atoms combine in simple whole number ratios to form compounds. That is also true. There's not any exception to this one. And atoms of one element cannot change the atoms of another element. So in chemical reactions, atoms only change the way that they are bound together. This is mostly true. We can have things undergo nuclear reactions where elements do change. So that is point number 4 is mostly true, but can be false under certain circumstances. So let's talk about subatomic particles. So sub, less than, less than atoms. We can break atoms apart. And cathode rays. So cathode rays, if you remember the old television sets, are cathode ray tubes. This is a cathode ray. And the cathode rays led to the discovery of electrons. And specifically, we found these cathode rays, and they're from electrons. And furthermore, Thomson found the charge to mass ratio of the electron, and in his experiments, and then talked about what this matters, and they are very low amounts of mass with this. So, and then further, the charged electron, the oil drop experiment, milk and oil drop experiment, found that there was a certain ratio of the charges, so that there was always the oil drops would have a charge, but he found a certain ratio of that charge, and from that we were able to deduce the mass of an electron. Mass of electron is 9.11 times 10 to the minus 31 kilograms. And then what formed after this was the next model of the atom. This was known as the plum pudding model. So if you are in the United States of America listening to this, I think a better contemporary way of describing this is probably the blueberry muffin model. So if you know a blueberry muffin, you have a big blueberry, and inside of it, you have a big muffin. Fumble on my words. You have a big muffin, and think of this big white muffin, but then occasionally you find these blueberries in the muffin. But the muffin is mostly this kind of white kind of cake in it. Then you have the blueberries spread throughout. Or maybe if you want to, maybe the chocolate chip cookie model. Maybe that's a little better. You have the big cookie, and then you've got the chocolate chips throughout. And the idea of you have this big region of positive charge, and then you have the electrons floating in this big region of positive charge. So this is the plum pudding model. And then, well, there's a problem. We have the plum pudding model that has this diffuse charge of this diffuse sphere of positive charge. This would imply that atoms are pretty much just, there's not a whole lot of structure to them. And then you have Dalton's atomic theory that it's atoms are like the ball pit when you were kids. If you have gone in the ball pit, atoms are just like these big hard spheres that you can't break. So Rutherford came along and says, you know what, we're going to figure out which one of these is right. And the way I'm going to do this is I'm going to take an alpha source, so radiation source, and your smoke detector works the same way. Actually, you have a radiation source, or the cheap smoke detectors work this way. They have an americium alpha source, and then it shoots out alpha particles. So Rutherford did this, had an alpha source, and then you can take gold and you can hammer it very, very thin. So he hammered a piece of gold, and then he hammered this piece of gold, and he put a screen around it. And let me remind you, this is the 19th century, so I remember hearing this story, and it just made me think of, like the difficult times of being a graduate student. Rutherford, he actually got one of his grad students to gave him like a clicker, like when you're going into Costco or something like that, and they have a person, with a clicker, going in there. He had a grad student said, "All right, you're gonna sit in this dark room, and I want you to sit here for an hour and click every time you see a flash of light, and then I want you to move." A little bit to the left, and then do it again, and just do this until you get an accurate reading of all the way around this detector. And so the grad student did that. And what the grad student found out was most of the particles went right through, but occasionally one would deflect. And so the grad student went and took all the data and gave it to Rutherford. Rutherford looked at this and said, "You know what? This is absolutely wrong. Like, it's not proving either theory right or wrong. There's a mistake. Do it again." And so the grad student went and repeated the experiment, and then brought the data to Rutherford, and Rutherford said, "This is still wrong. Do it again." And the grad student was like, "Hey, look, I know you're being a professor and you're in your tweed jacket, smoking your pipe and going out to coffee with your colleagues, and meanwhile I'm in the dark lab here, and this is right. I've done this experiment twice. This is right. So you can come and watch me do it." And then, of course, Rutherford was like, "Maybe he is right," and then thought about it, and then Rutherford came up with the idea of the atomic atom. So kind of disproved, even disproved it. So, well, this is the new model we use in Rutherford, and the idea was that there's this really massive center of the atom that could deflect the radiation, and but most of the atom was what he considered to be empty space. But it's not empty space; it's the electron cloud. The electron cloud. Well, electrons are not very massive compared to an alpha particle, so the alpha particle is going to be about 8,000 times massive as an electron. So electrons are also they're not dancing around. They're in they occupy a space. So even the area the alpha particle is going to go through is going to be small compared to that, and it's not the whole electron it's hitting anyways. But anyways, the very diffuse electron cloud around the nucleus. And so what's interesting about this is that Rutherford placed almost all of the mass of the atom into a small area called the nucleus. And this is correct. All right, this is absolutely correct. And the positive force is in the nucleus, and the negative charge is around it. So, and it's a very good model, and it was incomplete though. Because of neutrons. The positive force in the nucleus is also counterbalanced by another particle called neutrons. And so what? Why do we care? For the different forces, I know we haven't covered the fundamental forces, and this is more of a physics concept. So the fundamental forces are gravity, electromagnetic, nuclear strong, nuclear weak. Nuclear weak is actually electrostatic in nature. Nuclear strong. So the idea with the nucleus is that so protons and neutrons can engage in what's the nuclear strong force, and that nuclear strong force is stronger than the electrostatic repulsion of the positive nucleus, and that's the whole idea. But then the neutrons are needed to add additional force. And also later on, when we talk about nuclear chemistry, the heavier elements have many more neutrons because the neutrons need to have a stronger nuclear strong force to keep the nucleus bound together. So neutrons, and then and neutrons are slightly more massive than a proton. Actually, a neutron, if you let it sit, it will turn into a proton and electron. It'll beta decay into a proton and electron. And hydrogen, specifically the isotope called protium, no one calls it protium except for weird chemistry teachers, is one proton, and no neutrons. So this is the subatomic particles, protons, neutrons, and electrons. Protons are positively charged. Neutrons are no charged. They are found in the nucleus. Electrons are negatively charged, and they are found mostly in the electron cloud. Electrons can be in the the nucleus of the atom. They're typically not, though. Maybe the 1s orbital, but for electrons, typically they do not spend. They don't have much of their density. I almost said time. They're kind of a diffuse area. Their density is not predominantly found in the nucleus of the atom. It's mostly outside of the nucleus. And there's the masses. You can see a neutron is slightly more massive. And the relative charge, +1, but that's the charge of 1.6 times 10 to the minus 19 coulombs. Electron, -1 relative charge. And then the mass in kilograms, and the mass, the atomic mass units. Carbon-12 is, we give that as a 12 atomic mass unit. So the AMU is based off of carbon, or specifically carbon-12. So an element. So what defines an element? An element is defined by its number of protons in its nucleus. Frequently given the atomic symbol Z for the charge. So look here, the helium, for instance, has 2 protons, and carbon, for instance, has 6 protons. So if there is an element that has 2 protons, it's helium. If it has 6 protons, it's carbon. If it's got 1 proton, it's hydrogen. If it's 3 protons, lithium, and so on. And here is the contemporary, modern, however you want to say, periodic table. And the atomic number on the top, that's the number of protons. And we also give the elements names, and we also, we give them a symbol. And it's not just like, we don't say the element with 6 positive charges, we just call it carbon, for instance. And these elements have been found various ways, various cultures. They're not all Western. So, but for instance, potassium was found by the Arabic community, for instance. So, but, I already mentioned this, that the chemical symbol, and it's really for the number of protons. So which element contains 50 protons in its nucleus? So we gotta go back here, and the element with 50 protons is Sn, also known as tin. And the names Sn, many of them are Latin, so that's Sn for Latin. Some of it is common, and they're also different for different languages. So, for instance, like I used to live in Hungary, and sodium, I believe, is referred to as natrium there, and iron is called var. So, I mean, it just depends on your culture, and different areas are going to call the elements differently. So that's tin. And isotopes. So, if you are a fan of the show The Simpsons, like I am, the Springfield baseball team is called the Springfield Isotopes. Why? Because of the nuclear power plants, and they have the atomic symbol on them. Isotopes are something nuclear, and isotopes are elements that have the same number of protons but different number of neutrons. So neon, for instance, has 10 protons but can have 10, 11, or 12 neutrons. And these different neon atoms with different number of neutrons, these are referred to as isotopes. And something also that you might want to start noticing about isotopes, generally speaking, there's an even number of neutrons. So this is kind of above and beyond the class, but you're not going to see many elements with an odd number of neutrons, and if you do, they're going to be more unstable in a nuclear sense, and unstable nuclear sense means radioactive, and it's even more rare to find an odd number of protons and an odd number of neutrons, and that's because when protons or neutrons are paired with each other, they release something called the pairing energy, and so even numbers are always more stable than odd numbers for protons and neutrons. And then for the different isotopes, we have terrestrial. So here on Earth, there's a terrestrial abundance, and the periodic table, the atomic masses deal with this. So then we have the natural abundance as the atomic mass in the bottom. And we are getting better at this, and we actually are seeing variances in the abundance here on Earth. So some places, depending on where you're at, there's going to be ranges of isotopes. So let's look at this. And you have X, the chemical symbol, and then you have a top number, bottom. The top number is the mass number, and the bottom number is the atomic number. The mass number is the number of protons plus the number of neutrons. The bottom number is the atomic number. So looking at here, the different isotopes of neon. So neon 20, neon 21, neon 22. Neon 20 has the top number minus the bottom number has 10 neutrons. Neon 21 has 11 neutrons. Neon 22 has 12 neutrons. So, also, which I just mentioned there in the previous slide. And there's another way to present those data from the number of protons, the number of neutrons. And you can see here there's a natural abundance. And like I mentioned, the odd number, you can see the odd number is generally less abundant. You very rarely see odd numbers. You do see them. Deuterium, it's heavy hydrogen, has 1 proton, 1 neutron. Nitrogen 14 is a very common isotope. It's 7,7. But that's about the end of it. You really don't see the odd numbers, 2 odd numbers together after nitrogen, at least in any large abundance. Even going on to fluorine, it's going to have it's got the most stable isotope has an even number. So argon isotope has a mass number of 40. How many neutrons it have? Argon is element number 18. You don't have to memorize a periodic table. You always have a periodic table. If it's got 18 protons, that means it's got 40 minus 18, or 22 neutrons. So let's look at carbon. Carbon 12 is the most common naturally occurring one, and carbon 13 has a smaller amount. Which one of these represents the carbon 13 isotope? If you look at the red circles, let me count them. A and C both have 6. B has 7, so that's not. B is actually nitrogen. So it's going to be A or C, and then A has 7 blue blocks, and C has 6. So A is carbon 13, and C is carbon 12, and B is nitrogen 13. So, okay, but A is carbon 13. So losing and gaining electrons. So an element is defined by the number of protons. So if there's a charge that happens, it's the electrons that exchange. So a negative charge comes from the addition of electrons, and a positive charge comes from the loss of electrons. And positive charge ions, these are known as cations. So not cations, cations. And if you have a hard time remembering which one is positive, think of the T as a plus sign. So the T in cation is a positive ion. Negative ions are anions. So how many electrons are in the O2 minus anion? Oxygen is element number 8. Again, periodic table should be in front of you at all times when you answer this. 8 protons, and the negative 2 ion means that there is 2 extra electrons. That means it's 10. So what? Well, Mendeleev, hope I'm saying his name right, or Mendeleev, he is Russian. He's Russian, and he found, you know what? There's some repeating patterns to these elements, and he constructed the periodic table. He noticed these certain trends, and he noticed that they occurred, periodically, so in a repeating fashion. And so he arranged the periodic table. And not only that, he started predicting certain things. He predicted some sort of extra silicon. And later on, German scientists found it, or Winkler found it and named it germanium, after good old Germany. And we list them. We still have the use the same idea for the periodic table, and we have changed it a little bit. We The scientist that most notably changed it quite a bit was Glenn Seaborg. He specifically moved uranium from underneath was underneath tungsten. So it was he moved thorium and uranium and whatnot, moved them under from transition element to the actinides, and uh, and it turned out to be great. That was so. I think that Mendeleev had a better description of the periodic table. I think it more belongs to him, but sometimes people reward to reference Glenn Seaborg as the father of the periodic table. He's certainly the father of the modern periodic table, but the whole idea of periodic trims was Russian, and we have Mendeleevian because of that as well. So to honor him, and we have the different elements here. And a couple things to notice about this table: there's this step ladder, and so everything to the right of that step ladder is known as a non-metal, and everything to the left is known as a metal. And then there's stuff that's in between. That's kind of like a metal. Those are known as semi-metals, metalloids, or semiconductors. So they're kind of the properties of both. So what do I mean? So metals tend to conduct electricity and heat really well. They tend to be ductile. That means bendy. Non-metals tend to be brittle. They tend to be insulators, and so on. Does that mean all non-metals are insulators? No. Graphite carbon actually is a conductor. Also diamonds. So diamonds have a very high thermal conductivity. So it's a general rule. It's not an exact rule. And then semiconductors like silicon. Silicon's shiny. You can see that picture. It looks really shiny. It's kind of a weird metal, though. If you play with it, you touch it because it's kind of stiff. But silicon is weird because if it's sitting there, it does not conduct electricity. But then you put 5 volts behind it, and it will conduct electricity. And that's the whole idea behind our transistors. When silicon does not conduct electricity, we give that a 0 value. When it does conduct electricity, we give it a 1. That's our binary code, is based off of that 5-volt band gap of silicon, and that causes TTL, or transistor logic. So it's all based off of that. But so, and I just mentioned this, how we define them in metals, right? They're bendy, they're shiny, and they tend to lose electrons. Non-metals, they have various ranges. Some are gases, some are not. So, and there's various solids. Carbon has a couple different types of solids, for instance, and so does phosphorus and sulfur. And we also have several gases, and they tend to not conduct heat and electricity really well, but that's a general rule, right? They're not ductile. That's true as well. And they gain. They can also lose. Carbon can go either way. Actually, carbon can gain or lose electrons. So, but it's nothing like chemistry class, right? I tell you a general rule, and I tell you the exception of the rule. Well, it's not entirely my fault. Chemistry is an observational science, and it's an empirical science, and we're just reporting back to you. We have general trends, but there's also exceptions to those trends, and that's also what makes chemistry so much fun. I think it's fun, but I know it's frustrating for some of you students to understand. As you're learning this, you're like, oh man, there's a rule, and there's an exception to the rule, and there's another exception to the exception to the rule, and there's another exception to that rule under certain circumstances. And I think that's cool, but I know it can be frustrating. And I mentioned about the semiconductors here, semi-metals. I generally call them semiconductors. They're sort of conducting. They tend not to conduct, but you put voltage behind them or high temperature, and then they will conduct. So the periodic table, we have the main group elements. That's the S and the P block. It's the ones on the left and the right. I'll talk about that. And you have the transition metals, and then also the lanthanide and actinide. So the main group of elements, these are the parts on the left and the right, and then the ones in the middle are transition. And the rules to transition elements, they change a little bit for periodic trends. And we call the vertical columns groups or families, and the horizontal rows we called periods. And there's 18 groups and 7 periods. And the main number groups, so the main number are also, we'll talk about electrons later, that's the number of valence or outside electrons. And if you include the transition elements, you give them the letter B. So, and within a group, within a column, they tend to have similar properties, and specifically chemical properties. And so the last column on the right, these are known as the noble gases. They used to be called inert gases, but we can get them to react, so they're called noble gases. So why noble? Well, I know I'm speaking in American English. If you know more British English, the idea is the nobility were very stoic. So these are stoic gases, meaning like this is the best day of my life. This is the worst day of my life. You can never tell because I am noble. I'm not like a commoner that expresses my feelings. So the noble are the stoic, unreactive, unfeeling kind of things. So the noble gases, these are just don't react to anything. I mean, they can, but it's hard to get them to react. So, and that's what we use. So you can see we use them for various things. Then we have the far left, we have the alkali metals. So alkali metals, these tend to be very reactive in their pure form. And also the word alkaline. So this is actually came from what is that called? The Philosopher's Stone. The what is that called? The alchemists. Sorry, so I'm looking for the words here. Not so, especially something like an alchemist. The alchemy named this, and the idea with alchemy was you could turn lead into gold if you could find the Philosopher's Stone and get the elixir of life and have eternal life and have all the money you wanted. And but the word alkaline also means basic. So these are metals that if you throw into water, they make an alkaline solution, which means basic, which means not acid, like the opposite of acidic is basic, also known as alkaline. And alkaline, you also know alkaline batteries, right? So you have a lead acid battery that are typically in the cars, and you have alkaline batteries that are typically made of zinc and potassium oxide. So maybe you heard the alkaline batteries, that's where they come from. So but anyways, the alkali metals, these tend to be very reactive, and they form +1 ions as well. So that's a periodic trend because they have a similar properties in that way. They tend to be very light in terms of like low density, and they are also, like I said, very reactive. The alkaline earth metals, and so again, this is alchemy. These are metals that are alkaline, but they're not as soluble as the alkali metals. Soluble meaning dissolve in water. So alkaline earths tend to form precipitates. So these are things that fall from a solution. So if you took two solutions and you mix them together and you formed a precipitate, like, well, this is an element that can dissolve in water. It's alkaline. It's a basic solution. It's not acidic, but it creates this heavy stuff that falls. It's creating dirt. It's creating earth. So we call them the alkaline earths. So earth being like the earth, wind, fire, water. So that's where that name came from. So, and these tend to be very reactive, but they're not as they're not as reactive as the alkalis. And so there's beryllium, magnesium, calcium, strontium, radium. These are the alkaline earths. We don't talk about beryllium very often because it's very, very toxic. So we don't use it as much. And then halogens, so we're going to go back to the other side of the periodic table. This is right next to the noble gases. Halogens means salt forming in Greek. Sorry, Greek forming in salt. Salt forming in Greek. These are the halogens. And these also tend to be very reactive. They smell kind of similarly. Fluorine, Fluorine and chlorine, of course, are very pungent. They're all very pungent. It's not like you want to smell them. Fluorine smells kind of close to chlorine. It's has still has a very pungent smell, but it kind of smells almost like the ocean of sorts. Chlorine, of course, has a kind of pool smell in a way. Bromine, I don't like the smell of bromine as much. That's it's well, also frequently when you smell bromine, it's usually dissolved in carbon tetrachloride, which also stinks. So, and iodine, of course, whenever I smell anything, it gives me a headache. At least in their elemental form, right? It burns. So I don't recommend you smell them. I've never smelled acetine, but they fluorine and chlorine are gases, and bromine is a liquid, but it has a pretty low boiling point. And iodine is a purple solid, but and iodine also sublime, so you don't keep it capped, it's just going to evaporate away or sublime away. So which of these best turns to lead? Lead is, if you have the periodic table, it's underneath carbon. So it's a main group element, and lead is definitely a metal. So that's where it would be. And ions, so why do we have the periodic table? Well, it's to predict properties. And one of the properties to predict are what type of ions it forms. So generally speaking, the elements, they try to be like electronic structure of the noble gases. Because that's why they're noble. The gases with that electronic structure is just low energy. We'll talk about this in the future lectures, that why the energy structure is low energy, and so things tend to go towards low energy. So metals tend to lose electrons to be more like noble gases, and nonmetals tend to gain electrons to be like noble gases. Noble gases are already there; they don't need to do anything. And this is basically what I said. And then the number 8 in the octet rule, of course, this will come in later. Except for hydrogen, helium, they can go for 2. But the number 8 comes from the s and the p orbitals. There's 6p and there's 2 s's, so 6 plus 2 is 8. And that's where that comes from. And we'll talk about this more later. And so you can see here the alkalis and the alkaline earths. Alkalis tend to lose 1 electron. Alkaline earths tend to lose 2. So losing electrons gives you a positive charge. So alkali is going to lose 1 electron. Alkaline earths lose 2 to get the plus 2. Then the halogens tend to gain 1 to be a negative 1 charge. Oxygen family tends to gain 2. Nitrogen family gains 3, and so on. And then they do that so they can be like the noble gas configurations. And you can see hydrogen is in both spots. Hydrogen should be in a category on its own. It's not really a alkali metal or a halogen. It's kind of its own kind of thing. So moving topics, talk about atomic weight. And again, this is here on Earth. So here on Earth, there tends to be there's some variations, but generally speaking, there's a certain abundance of each element. And we have the ratio of those isotopes to give the atomic weight. So for instance here, chlorine is about 75% chlorine 35 and about, I almost said 25, but 75.77, sure, I'll use the exact numbers, and 24.237% chlorine 37. So you take the masses and the relative abundance, and you will be given the abundances and then the relative masses here. So in a problem like this, and you can look them up. I have a chart that I can find all the relative abundance and atomic masses of each nucleotide. So nucleotide is just the number of protons and neutrons for every element. So we know all this stuff already. And then the weighted average there into 4 sig figs is 35.45. So, and the way you figure this out is the fraction of each isotope times the mass of the isotope, and then you sum them together. That funny looking E thing with the underneath that is the capital Greek letter sigma, and that means sum. And the N is just a number. So that is a mathematical formula telling you to sum up each of that fraction of each isotope and then add them all together. So that is a sum function. So to give you to kind of give you this idea of how this works. So from previous, we have carbon 12 is 99% carbon 12 and it's 1% carbon 13. And the mass of carbon 12 by definition is 12. And carbon 13 is a little bit more massive, 13.0034. So without doing the calculation, which is the closest to the atomic mass of carbon, it's 99% carbon 12, so that's going to be really close to 12. It's 12 right there. So we can also look at the mass of things using mass spectrometers. So mass spectrometers, and it depends on the precision. You basically charge particles and then you bend them using something like a magnetic field or accelerate them using like electronic field. There's a couple different types of mass spectrometers. This one here has a magnetic field to separate them out. You don't need a magnetic field. You can separate an electronic field and then use time of flight. So just by when it hits the detector as well. So this one here will do by the distance that you bend things, and the more pixels you have in your detector, and also if you go over a longer distance, you can have more resolution on your mass spectrometer. And so well, let's change topics yet again. And we're going to build it to what's known as the mole concept. And we have a very colloquial term we use, dozen. Dozen means 12. And so you can use dozen very frequently. You can have a dozen eggs, for instance. And you can even have a half a dozen. You can have 2 dozen. So you can use multiplications and also fractional parts of something. And atoms are really, really tiny, so we needed some number that's really, really huge to describe the number of particles. And also, we can count number of particles by weighing. I know Las Vegas has changed a bit, but I've been to Las Vegas, and when you win the slot machines and you have all these quarters, you can bring them up to the countertop. And what do? They weigh it, and then they give you like the cash, or they give you a voucher or something like that. So you can weigh things by counting them as well. So weighing things like coins, because there is some variation, but coins weigh about the same each. And atoms, though, these are much more, at least a specific nucleotide or isotope, if you want to do that, say that. I'm sorry, I'm using the more advanced terminology. They're all going to weigh the same. But we can measure things by weighing them. And like a dozen, we have to come up with a specific number. We have something called a mole, and that's Avogadro's number. And this is a mole is 6.02 times 10 to the 23rd. So you look at this, it should tell you 2 things. First thing to say is like, that's a huge number. 6 with 23 zeros after it. That's a huge number. The other thing it should tell you, like, man, atoms must be really tiny. So atoms are really tiny, and moles are a very huge number of particles. And often, so you'll see mole, or sometimes referred to as mole, MOL. The mole right now, as I'm recording this video, is based off of carbon 12. 12 grams of pure carbon 12 is a mole. We may change the mole to silicon, based off of silicon, and also turn the kilogram into silicon. So right now the mole is based off of carbon, and kilogram is based off of platinum, hunk of platinum. So this may change. So couple things. We can use the mole for anything. The mole is just like a dozen. A dozen counts for 12, and a mole is that number 6 with 23 zeros after. 6.02214 times 10 to the 23rd. It's that many things, that many units. Just like a dozen is 12, that's a mole. You can use it to count in grains of sand. You can use it to count in dollars. But that is the base unit of that. It's just a number. And but as I mentioned before, so what? Well, we base this number off right now based off of carbon 12. And then we can convert between things. And this conversion factor is going to be used in subsequent classes. So we're going to talk quite a bit about this, and then using dimensional analysis to solve quite a few problems using this. And we're just building up now talking about the mole concept, because the mole concept is going to be used for, well, it's going to be used the rest of well, pretty much as far as you're in chemistry, you're going to be talking about moles. And we can count things, and we already mentioned this, by weighing them. And a mole of atoms is the molar mass. And that's the atomic mass. Well, it's in the bottom number on the periodic table. So the atomic mass. And so, for instance, and this is the bottom number on the periodic table, almost 27 grams of aluminum is a mole of aluminum atoms. 12.01 grams of carbon is a mole of carbon. 4.003 grams of helium is a mole of helium. And this corresponds also to all the naturally occurring isotopes that you have in the different elements. So with the 1% or so of carbon-13 is the reason why it's a little bit heavier for carbon, not just 12 grams of carbon, for instance. And we can convert back and forth, as I mentioned before, using dimensional analysis. So we will talk more about this later. And now with this class, of course, we're doing lots of problem solving. So when you're trying to solve these problems, look at the given information, look at where you need to go, and then you got to deduce what you need, and also then the conceptual plan on how to attack the problem, how to get to the end. And many of these elements, if you want to go from the mass of an element to the number of atoms of an element, you're like, okay, well, how do I get, so I have the mass of an element, what do I need? I need the moles. So the moles is the number, I get that number from the periodic table, and then I can use Avogadro's number. Okay, so join me next time as we go to chapter 3.